I hope that's the right. Did that work?
I don't think that pins him for everyone.
Oh, that doesn't?
I think that's just you.
Oh, I see.
What is this concept of pinning?
Just
It makes your video front and center.
I see. Okay.
but maybe that's not necessary. Then people can.
Isn't there an automatic feature where who's ever speaking?
Yeah, it does that. I forgot. Yeah, so that'll be fine. All right. So let's get started. That'll work. Yeah, so I want to wish everyone a happy new year and hopefully a better year. And welcome everyone to the first Western Hemisphere Colloquium on Geometry and Physics of the year. Everyone will remain, of course, muted, and you can put questions in the chat during the lecture. And then after the lecture, you can use the raise hand feature and we'll have question and answer after the lecture. So we're very happy today to have Mike Freedman from Microsoft in Santa Barbara to talk to us about quantum codes and systolic freedom.
Thanks, Dan. It's really an honor to be here, wherever here is. And you know, if you have a way, I don't know about this raising hands thing, but if you have some way of just shouting and interrupting, feel free. So as Dan said, the subject is systolic freedom and quantum codes. And I'll tell you what both are. So starting with systolic freedom, the subject really begins with the definition of a systole, a 1949 paper of the analyst, the complex analyst Louvner, in which he showed for a torus with any Riemannian geometry that L squared over the length over the area is less than 2 over the square root of 3, where L is the length of an essential loop, essential simple closed curve on the torus. So this is for the torus. And there's a similar inequality, which is proved shortly afterwards, where the number is now pi over 2. And that's not for the torus, but that's for the real projective plane. And it became a whole subject. People still write papers on it. It has a number theoretic flavor, higher genus, and so on. So the idea is, you know, in a slogan, the shortest loop can't be too long. So it's a Riemannian statement. If you have some fixed topology like the torus, and you play around with all possible Riemannian geometries on it, and if you normalize the length squared by dividing by the area of the surface, then you can't arrange that the smallest loop be too long. The extremal example which realizes this estimate, actually it's equals there, for the hexagonal, if you take the regular hexagon and you glue up opposite sides to make a flat torus, that's the extremal example. And of course, this one's the round sphere. Now, Gromov in the 90s breathed a lot of life into this subject with some beautiful examples and counterexamples. And rather than kind of give you the definitions bald, I think I'll just go through Gromov's most basic example in which to learn the definitions of what systolic freedom is. So Gromov's example is a family of metrics on S3 cross S1, where we just take the sphere of radius r, the 3 sphere of radius r, we cross with the interval of length 1. So now we have a Riemannian 4 manifold, and we blew up the opposite boundaries by an isometry, orientation preserving isometry, which says S at 0 is equivalent to minus S, the antipodal point, at the one end. So I just glue the two sides together by this twist. Now the twist is isotopic to the identity. It's orientation preserving since this is an odd dimensional sphere. So these are all metrics on the same manifold, if you like. And let's just think about like lengths and areas. So, so I'll give you a statement. The statement is, and then we'll do a calculation which will show what the definition of the statement is. So it said that with integer coefficients, this example obeys 3,1 systolic freedom. So that's a mouthful, but what does it mean? It means if you look at with integer coefficients, we'll look at the smallest cycle in dimension 3. And by a comparison argument, it's called calibration with sort of the fiber sphere, you can see that no cycle, because you can project on it, no cycle can have less area than that fiber sphere. So the 3 volume scales like r cubed, the length of the sphere, and that's the 3. And the 1 volume, the length of the shortest essential loop, well, it isn't constant because of this twist. In order to close a loop, you have to not only go across the unit interval, but you have to go halfway around the sphere. So that scales like r. And the 4 volume of this gadget is just, this is constant, so it's just scaling like r cubed. So this ratio is r to the 4/3 power, which is written as r to the 1 plus alpha, where alpha equals 1/3. And this is said to have systolic freedom. And even more so, you can quantify it by saying that it's Z31 power law systolic freedom, because this ratio, the numerator was a power of the denominator greater than 1. So that's a very strong systolic freedom. Sometimes systolic freedom, the numerator is only bigger than the denominator by a pitiful log factor, polylog, something like that. And that's distinguished as kind of a weaker form of freedom. Now, in order to make sense of how much freedom you have, there's an obvious scale discussion that needs to be made, but it's very simple. You see, if I were to either dilate or shrink this metric by a linear factor of L, then I would put an L to the 4th in the numerator of this expression, L to the 3rd for this and L to the 1 for that, and an L to the 4th in the denominator. So of course, mathematically it cancels, it doesn't change the ratio, but it gives you a different impression as to what power you would have to raise the denominator to get the numerator. Do you see what I mean? So in other words, if you were allowed to rescale with an arbitrary L, you could make this 1/3 be much larger if you made L small number, or much smaller if you made it L a large number. So in order to be able to speak about power law versus, say, log systolic freedom, the convention is you normalize all metrics to have all the sectional curvatures O of 1. So things can neither be very positively nor negatively curved. That's the normalization we take on all the metrics. And we don't even have to normalize in this family. All these metrics are O of 1 anyway. I mean, as R gets bigger, the curvatures go to 0, but that's fine. The important thing is that they don't blow up. Now, I don't want to let go of this example just yet. I want to convince you that if you tried to put a 2 here, if you tried to make the same discussion with Z2 coefficients, then it wouldn't work. There'd be no freedom of any kind anymore. So what's the deal with Z2 coefficients? So if you look at this example kind of pictorially, for large R, where you see is this big sphere, and very close to it, 1 unit away is another copy of itself. And it can reach around to its antipode just by moving this small distance. So it's possible to take like a patch on the sphere, which is pretty big. And then this is like a patch centered at the point S. And this is like a flipped over version of the sphere. So this is a patch now centered at the point minus S across 1 or something. Well, I'll just say minus S. And now you could cut out these 2 patches and put in this tube. And that's illegal operation if you have to take orientations into account, because this tube wraps around the circle direction and it only gives you a non-orientable cycle. But if you're studying with Z2 coefficients, it turns out that you can make this power here 2 instead of 3. You can cut out enough garbage and its antipodal images so as to see that there's nothing exciting going on in this example with Z2 coefficients.
Mike, was there a log missing before in the ratio?
A log?
You had r to the 4th divided by r cubed is r.
Yeah, yeah. So in the numerator I have r to the 4th, and the denominator I have r cubed. So the ratio is r to the 1st. Oh, sorry, well, I raised the alpha 1 plus. This ratio is r to the 4/3, right? R to the 4 divided by r cubed is r to the 4/3.
Is it?
Oh, sorry. Sorry, it's not. Thank you, Dan. Yeah, this ratio is r to the 1, but right. Yeah, I'm sorry. I misspoke. The 1/3 is you ask the question. You express the numerator as the denominator. This is just the conventions of the subject times the power of the denominator, which is alpha.
Ah, okay.
So in this case, the numerator is r to the 4, and you express it as the denominator, which is r cubed.
To the power.
Right, to the times the denominator raised to the 1/3. And this is the alpha.
Okay.
Sorry.
No problem. Thanks.
And now with this straightened out, what I said about scaling probably makes much more sense. That this funky way of thinking about it, how much more do you have to increase by what amount, like a power or a log or whatever, how much you have to increase the denominator to make it equal to the numerator is upset by arbitrary rescalings. That concept would be lost if you allowed it arbitrary rescaling.
Yeah,
So
that's better.
So you normalize to constant, to bounded curvatures. Sorry about that. I'll try not to repeat that.
Okay, thanks.
Okay. Okay, so Gromov actually highlighted this in his papers in the late 90s, this open question of whether there was ever systolic freedom with Z2 coefficients. He produced many examples with integer coefficients. And I became interested in this question in 99 when I started thinking about quantum computing, because systolic freedom is an issue with quantum codes. So let me explain that connection, but just note that in 99 and then also in 2003 with Feng Luo and Myers, we wrote some papers finding the first cases of Z2 systolic freedom using geometric constructions of three manifolds and some arithmetic theory on surfaces. You know, it's well known that surfaces have kind of beautiful geometry, right? Riemann surfaces that you can find surfaces of area A whose injective radius is log A, basically. So it's very far. The smallest closed loops are very, very long. And this is kind of an interesting systolic thing in 2 dimensions, but it's not ready in 2 dimensions to produce a systolic ratio but in 3 dimensions, you can make certain mapping torus constructions out of automorphisms of these surfaces. And that's what we did to produce these examples. But I need to now fill in this story about the toric code to tell you why this is anything related to quantum computing or quantum error correction. So there's a famous code due to Kitaev called the toric code. And in our context, the toric code will be an example of a low density parity check CSS code. This is names of people, Calderbank, Steen, Shor, low density parity check. This means that not only are the code words short, but no bit or qubit occurs many times in the checks. There's a bound to how often the 10th qubit is ever looked at. And I'll be saying more about these codes in a moment. Low density turns out to be a sparseness condition, which is related to bounded geometry, bounded curvatures when you turn it in, when you think geometrically. So what is the toric code? And it works on any surface, and you can generalize it to work on manifolds. But let's think of it in its simplest incarnation. You take the torus and you give it a cell structure, and you might as well just choose the simplest cell structure, some kind of rectangular grid. And you write down a Hamiltonian, and the code is the ground state of the Hamiltonian. And the Hamiltonian has 2 terms. It's minus summation of all the vertices of a vertex term, which is called star term, minus the summation over all the plaquettes. Plaquettes is physics talk for 2 cells of the plaquette terms. And the definition is that the star term is the product over all, okay, I didn't say this. The qubits are parameterized by the set of edges in this cellulation. So to each qubit, to each edge, you associate a Hilbert space C2, and then you make a bigger Hilbert space by tensoring them all together. And this Hamiltonian is going to act on this space. And the S term is the product over all edges which meet a vertex of the poly X operator on that edge. And the plaquette term is the very similar looking formula. It's all the edges that are in the boundary of a plaquette of the product of the poly Z operators. So this X operator in a basis, this is the up-down basis, or zero, ket 0, ket 1 basis. You just take any basis for the Hilbert space C2 fixed once and for all. And this is sort of the knot operation. That's a unitary, or it's a Hermitian and unitary. And Z, so this is called bit error or bit flip. It flips, 0 to 1 and 1 back to 0. And Z is more subtle, it's more quantum mechanical. This is this matrix, which is called the phase gate. or phase error, phase flip. What it does is it does nothing on ket 0 and it reverses the sign, the phase of ket 1. So the only thing you need to know about these are these operators anti-commute with each other. And because stars, you know, the vertices in this picture, stars and plaquettes, they're either far apart and they obviously commute with each other because they're on disjoint tensor factors, or if they're next to each other, then they share 2 qubits, 2 edges, so they anti-commute twice. So all these terms actually commute with each other. And that's, you know, basically what a CSS code is. It's a bunch of words, or some of the words are written with just X's. So you just use these local operators on some of the qubits. And the other things that are operators that just use the Z's on other bits of qubits. And the fact that they commute with each other is the condition that if there's overlap, they overlap an even amount, even number of qubits, then they commute. And the code space is the ground state, which, if you follow through the notation, just means it's the intersection of all the +1 eigenspaces. That's why this is sometimes called a stabilizer code. +1 eigenspace means it's the subspace stabilized by that operator. And if you have, and you know, in ordinary non-quantum mechanical coding theory, they talk about parity checks, you know, like it's to see if something is a code word, you check that certain linear combinations of the entries add up to 0. And those are called the parity checks. And basically these CSS codes are like 2 sets of parity checks. One is done in the position basis and the other is done in its Fourier dual basis, you know. So these 2 operators, X and Z, are conjugated one to the other by Z2 Fourier transform, a so-called Hadamard matrix. So, you know, basically quantum error correction and quantum coding is a kind of an exciting version of classical coding where you have 2 codes going on at once usually, you know, one in position and one in momentum. Okay, but now what's an error? How, you know, if you do an operator, if you do a local operator, what happens is the ground state. Yeah, so first I should tell you what the ground state looks like of H. It turns out that the ground state is C4. It's a 4-dimensional Hilbert space. And you can think of it as equal to span, the complex span of the Z2 homology of the torus. So the first homology of the torus with Z2 coefficients is just, it's Z2 plus Z2, so it's 4 elements. So another way of saying that is there are 4 possible loops up to Z2 Bordism you can draw on the torus. And each of these 4 loops is a basis for the code. And basically the way this works is the vertex operators, the star operators, the only way you can be in the +1 eigenspace of this is if a parity condition is satisfied. If your state is a basis state, it better have an even number of ups and a, oh, maybe I'm speaking in the Z. Yeah, I think I'm, there's a duality here, and I can talk either, I can put the Z here, the X here, and I think the words I'm saying are now the Z's on this side, because if we switch the Z's and the X's here, which is just a basis change, that's the way I normally think of it. On the vertices, every time you have a edge coming into the vertex labeled 1, that counts a sign, and an even number of edges at the vertex mean that the total sign multiplies out to 1, and you don't get any penalty from the vertex term. So to pass the test at each of the vertex terms, you have to have closed cycles, closed mod 2 cycles. Otherwise, you get charged an energy penalty. And then to pass the other test in the dual operators, you have to have the same weight on a cycle as if you fluctuated across a square, because that's what the other operator does. It fluctuates across a square, it creates a linear combination. So that reduces to homology because it's all the cycles, but homologous cycles have to have equal weight. So the ground state consists of equal weight superposition of cycles within a homology class. That's the basis for C4. And if you do a single X or Z operation on an edge, what happens is you create anyons. You create an excitation over the ground state. What an anion is in this context, it's a pair of vertices which see odd instead of even, odd instead of even a contribution from the cycle. You break so if you do like an X operator on this, you'll break the cycle and you'll have 2 points which are endpoints now. So the reason these codes can be used to correct errors is if something is trying to be a closed cycle on a torus that's like 10 links around in the shortest direction, and you make a mistake and a cycle gets broken somewhere, you can guess how to fill it in without changing its homology class. There's sort of a natural guess. You just put back what's broken. Now, if you break 5 bonds, half of 10, you might be confused about how to fill it in. So roughly you can correct half the distance of the code. The distance is the shortest logical operator, the shortest operator that can act within the code space. And the shortest thing that can act within the code space is a string of X's or Z's that goes around an essential cycle on the torus. And what that type of operation will do is it will change the value of the encoded information from one homology class to another, like twist it around the cycle. So if you're trying to make a good code that can correct a lot of errors, you're interested in this systolic property, the shape of the surface it's encoded on, because you don't want any narrow cycles. That's where information can kind of leak out. So these arithmetic surfaces with all cycles are like log size. Those are kind of attractive if you're trying to store a lot of qubits. And that was sort of what was on my mind in '99. Well, I just kind of forgot about all this, but then I got an email from Matt last fall saying, you know, the coding theorists haven't forgotten about this problem and they've been busy. Well, you've been lazing about for 20 years and now we have much better codes. We have codes that show a polynomial, quantum codes which show a polynomial freedom. So I didn't explicitly say what freedom is on the code side, but remember I defined the geometric freedom as sort of the area in dimension P, the minimum area times the minimum area in dimension Q, divided by the volume in dimension D. It was this ratio that I used to define freedom. If this diverged, this was freedom. And we'd have to talk about coefficients. Well, what replaces this in coding theory is you talk for these CSS codes, which are X and Z stabilizers, is this becomes the area, this becomes the smallest
Mike, the question?
X stabilizer, and this is the smallest Z stabilizer. And this is the number of qubits. Yes.
This log behavior of the systols you mentioned, isn't it accompanied by the dual cycles going, small vanishing?
No. It's a win-win situation. It's very exciting. You can find up to a constant factor. You can find exactly what the constant is the subject of much research, but you can find a surface of genus 1,000,000 so that the smallest, you can find a hyperbolic surface of genus 1,000,000 so that the smallest essential loop is a log a million.
Okay.
That's amazing. I mean, it's not like Euclidean geometry, where if you have a rectangular torus of area 1, in order to make one side long, you make the other side short. It's different from that. Yeah, so in the coding world, this idea of freedom, and you can see why it would be good, is to have a code so that the smallest logical operator that can act in either the with either X or Z generators is pretty big in this compared to the number of qubits. So it's like a way of saying it is, in order to have a mistake which can't be corrected, you want for a reasonable number of qubits, you want the uncorrectable mistakes to be large. And there are 2 types of uncorrectable mistakes, and they should be multiplied together to get something to compare to the number of qubits. So, just like in the Livner formulation, there was an L squared, here there are cycles in dual dimensions, and they should, what the exciting thing is if the smallest X error, and not error, the smallest X operator that operates on the code space, and the smallest Z together, when you multiply them, are much larger than the number of qubits. That's what's exciting. And that's what they found 6 months ago. So when Matt informed me of
Mike, there's another question.
Yeah.
So, I mean, I realize you're trying to save some time by cut it with simple explanations, but the statement that there are 2 kinds of errors is obviously oversimplified quantum mechanically in general. But, I mean, for this particular code, you know that X and Z errors were a convenient basis, but I assume you must have some general formulation.
Well, yeah, I mean, the general statement is that it is sufficient to choose this dual basis, which X and Z is a convenient language for, and correct all errors with respect to both sets of, with respect to both bases. And then that will flush out all the errors. So that's an important theorem in error correction, that you can divide the problem into these 2 classes. So Matt asked the question whether we could go backwards. I was very pleased 20 years ago that Riemannian geometry allowed the discovery of a better quantum code. But then, that pleasure evaporated when coding theorists found even better code. So then the challenge was, well, instead of using Riemannian geometry as a way to improve codes, can we use coding theory to make new examples in Riemannian geometry? So that's what the paper with Matt that's on the archive, that's what we do. And let me explain the formalism. Let me write ZQX for this is qubits. These are the X stabilizers for CSS code. And these are the Z stabilizers. And I'm thinking of these as, well, modules over Z2, or you could call it F2. So this is what we're given, and it has 2 boundary maps. And the boundary map is that boundary ij is 1 if the ith stabilizer, so that would be like my star operator. If the ith stabilizer contains the jth contains the jth z. So in other words, the zj operator on the jth qubit, if that occurs in the I stabilizer, then we just put a 1 there, otherwise we put a 0. And for boundary prime over here, it's exactly the same statement, but it's equal 1 if and only if the I stabilizer contains the jth x. So, I mean, this is a very simple observation. The observation is that the requirement that the x and z stabilizers commuted with each other is this even overlap. And the even overlap is exactly saying that boundary squared is 0 as a Z2 chain complex. To just think of this simple definition that these boundary maps are sort of incidents, recording incidents of indices, and the even overlap condition is that this be a complex. Now, if we want to try to build a manifold using this complex, Z2 coefficients are not desirable. We'd like to have Z chains. So we'd like to lift this to Z. And there's a naive lift. So we can replace each module over Z2 by module over Z. And we can replace each 0 in Z2 with a 0 in Z and each 1 with a 1 in Z. But if we take the naive lift, then the lifted composition will merely be even. We don't know that it'll actually satisfy the definition of a complex. That's one problem. Another problem is in the lifted map, the homology and cohomology of the complex may contain odd torsion. It might arise. And a third problem, which is one has to deal with, is sparseness. Suppose the original chain complex is sparse because it came from one of these low density parity check codes. The question is, can you lift it and keep it sparse? Well, the naive lift will certainly still be sparse because it only has the same number of non-zero entries. But it's not clear what happens to sparseness in general if we organize the lift so as to make it actually a complex over Z. So in other words, if we make the even go to 0 here. So I should say that 1 is okay. We can always solve 1. And the way this is done is you can do row and column operations on this Z2 complex in order to put it into a very standard form, sort of block diagonal 0s and 1s. And then in this block form, you can use the naive lift, and then you can undo the row and column operations. Now, it turns out that it's a very subtle problem whether sparseness is preserved or whether you might get very large odd numbers when you undo all these row and column operations, which would be non-sparseness over Z. It turns out sparseness is okay for the new codes that Matt was involved in discovering. So this is okay for the Hastings, Ha, O'Donnell codes that our paper is based on. And 2 probably is okay, but that's ongoing calculation that's not decided. So you'll see the impact of that going on. But now, once we have a integer complex, which is still sparse and a real complex over the integers, we can just try to formally turn it into a cell complex. So we can say that maybe Q is dimension J cells, and these are dimension J minus 1. Formally, these are J plus 1. And this is appealing because this is like the toric code. Remember, in the toric code, we put the qubits on the edges, and we put the x's on the vertices and the Z's on the plaquette. So we try to build something like this, but there's a question, what dimension should J be? And the first thing you notice is J better in general be greater than 1. In other words, this shouldn't be 0 cells, 1 cells, 2 cells in general, because there may be high multiplicities. It may be that a particular qubit occurs in many, many X stabilizers, and as opposed to the toric code case, when it only occurs, the qubit only occurs in 2 star stabilizers. That fits well with the fact that an edge has 2 ends. But suppose you had a code where a qubit occurred in 20 X stabilizers. Obviously, you don't want to model that by a 1 cell. So it turns out that it's good actually to set J equal to 4 or higher, but 4 works. And the reason is that our construction will need, for various reasons, 1 and 2 cells, and we don't want those 1 and 2 cells to kind of get mixed up with cells in these 3 dimensions, which is where we're going to make this systolic analysis. So the way we build a manifold from a lifted complex, starting with J equal 4, is, well, these are going to be 3 cells. We call them cells, but we're not actually, you see, in ordinary topology, you'd start with a base point, and you'd like glue all the cells to the 3 cells to the base point, and you'd have a bouquet. But this is a terrible idea from the point of view of low density or bounded geometry. You don't want to glue millions and millions of things to one point. So you have to do something more free floating. So this X is actually a disjoint union of S3 cross, well, we're going to make an 11 manifold ultimately, D8. It's a large disjoint union, 1 for every stabilizer. Q is again a large disjoint union of 4 spheres minus many punctures cross D7. And this boundary map is modeled on the lifted map. And what it does is it takes these punctures one at a time and maps them degree plus or minus 1 to the appropriate sphere according to what the code dictates. And then the last thing here is S5, but now we have to attach it to the, we have to have some, create some boundary which attaches to the cycles in here. So the cycles in here are represented by these punctured 4 spheres stuck together in some complicated arrays. So the cycles that we come up with actually have the topology of large disjoint unions of large connected sums of S4 of S3 cross S1s. That's what happens when you start gluing punctured 4 spheres together like Tinker Toys. You get these connected sums of S3 cross S1s. These are the cycles here, sort of like the squares in the toric code. And we need now 5 sphere minus, I'll call it a graph, a neighborhood of a graph. To glue onto these cycles.
Mike?
Yeah.
So you've sort of erased it now, but well, actually, I have 2 questions. I have a question about what you had on your previous quote board. You talked about the issues of lifting from characteristic 2 to characteristic 0.
Yeah.
Did the HHO codes, are they wedded to characteristic 2? Or, well, I mean, because for many algebraic constructions like that, at a minimum, there can be a characteristic P version, or in some cases, it goes all the way to a characteristic 0 version from the algebra, depending. I don't know. I mean, it seems like it would be preferable to try to fix the problem at an earlier stage rather than to import the codes that they make.
Well, I mean, this is subject is very much in flux. Actually, just last night, I got an email from Matt saying that two other quantum coders, Pantalev and Kalachev, actually now have better codes than HHO that increase the systolic freedom from approximately 1/4 to 1 in that term. So alpha goes from 1/4 to 1. So I'm not directly answering whether you can do this with Q-trits. I don't know the status of these codes. I know the form of them. They're called fiber bundle codes. And I suspect that they can be done with trits and so on. So I don't think that they're wedded to 2. But I think it doesn't matter what finite Hilbert space you start with, there's still going to be a lifting problem to the integers.
Oh, no, no, no. What I mean is the LDCP, the CSS rules can just be stated directly in terms of chain complexes so
Okay.
that you can forget the qubits and just treat such a quote code as a chain
Yeah.
complex construction. And
Well,
then maybe the algebra can give
okay.
you characteristic 0.
I understand. Well, I use characteristic with respect to fields, really. This is the integers. Are we okay on that?
Well, right. But I guess I meant you can have integral constructions that look a lot like
Okay, I
codes.
understand what you're saying now. Like, for instance, you could imagine codes on harmonic oscillators instead of qubits.
I don't know if that fit codes and harmonic oscillators would fit precisely, but at least as a rough analogy, you can try to.
That's a good question, and I just say there's a lot of research and researchers on this, and I actually don't know the answer to that question. So I think the bag of codes is in flux, and we just grabbed into the bag, took the best code, and solved the lifting problem ad hoc.
So anyway, my other question, and then I'll be done with my questions, is for what you have on your board right now. I just to have a rough idea of why you wanted approximately 10 dimensions. I mean, high single digits or 11 is maybe close enough. Is it just to have handles where there's room enough for both a co-core and a core, or a link and a co-linked, to each be 4-dimensional, or each be maybe 5-dimensional for?
Yeah, let me, I will explain why we're pushed to these dimensions. So I kind of gave the first bit of a feel for this, of why we don't just say 0, 1, and 2. And that's because an edge only has 2 boundaries, right?
Right.
Okay. Now, one thing I want you to notice is the generators for these modules, which I'm calling cells. They're actually little handle bodies themselves. Like, because of the way things have to attach, this is not a disk. It's a sphere minus a disconnected graph. So it itself actually has 1 handles and 2 handles as a relative handle body, because the graph has pi 0 and pi 1. So the complement is a handle body. This has, as a handle body on its boundary, this has handles of index 1, 2, and 5, okay? And similarly, because we had many punctures on these to go around these free-floating spheres, this is actually a handle body with handles of index 1 and 4. And this is, of course, a handle body with index 3 and 0. Now, the point is, in this construction, we already have handles running around occupying these low indices, 1 and 2. And I wanted these to be in indices 3, 4, and 5, just so there would never be any confusion whether a handle of a given index came from one of these subsidiary reasons or whether it's part of the code translation.
Mm-hmm.
Because I have to understand, at the end of the day, all possible cycles that are made from like the 3 handles or the 2 handles. And if some of the handles are coming from these subsidiary reasons, they're going to then mix in with the generators that I'm interested in from the code. So the very simplest thing is to shift the dimension up enough to just separate the issues. I'm not sure to what extent that's absolutely necessary, but it turns out that fairly high dimensions, 9 and higher, actually is convenient for recognizing the final manifold that we make. So at the end of the day, the target with the correct coding input is to produce a sequence of metrics on S4 cross S7, which exhibits a very good power law systolic freedom over Z2. That's kind of the punchline of the paper. And in order to analyze the manifold, we also wanted in the sort of surgery dimension domain.
So you have handles, you're throwing in handles for different reasons, and you don't want the different types to interfere with each other, so you place them in different dimensions. So it sounds then like you're not particularly optimizing your dimension, but
No, we're not. No, we're not. This was a quick pass. And in fact, dimension 11 was very attractive because it's the string theory dimension. That's a joke.
I'm not a string theorist, but I know some in the audience, and I think they would appreciate that you are just joking. Okay.
Yeah, no, those were good questions. Right, because if you walk down a long corridor to get to a door, you want to have some understanding why you waited to that door and why the other doors in the corridor were closed, you know. So yeah, that was actually very, very useful. So we're actually ready pretty much for the punchline of the proof, even though it looks like I haven't gotten that far. So basically, here's the plan. We take the code, we lift it to an integer complex, we make sort of a handle structure, but it's a goofy handle structure. We make this goofy handle structure, which contains subsidiary lower handles, and it fits all together as some 11-dimensional manifold with a boundary. And we turn it upside down and double the thing to get a closed manifold. And that's the manifold on which we're going to exhibit systolic freedom. And it's very much like the toric code. There'll be 4 cycles coming from the qubits. So just like in the toric code, the edges fitted together to give 1 cycles. Now the edges are 4-dimensional, they're the qubits, and they're going to fit together to give 4 cycles. And then the dual operators in the toric code acted transversely, and the transverse errors, you know, will fit together to form 7 cycles. And what we know from the coding theory is that cell-wise, both the 4 cycles and the 7 cycles are enormous. That's what those inequalities that I've erased said. It said that any logical operator has to be an enormous 4 cycle or an enormous 7 cycle if we restrict to logical operators made of X's and Z's. Well, it doesn't look like we've proved the theorem, because all we've done is we've created a manifold with some explicit cell structure. And all we can say is with that specific cell structure, any cycle consisting of these specific cells has to be large, or these specific cells has to be large. How do we know that there's not some other Riemannian chain of dimension 4, which is very much smaller in 4 volume, that doesn't have much to do with these clunky cells? You know, it might be that the cells are like this. Or I should keep my color coding constant. It might be that the cells are kind of inefficient, like a staircase, and that we can find some Riemannian cycle that goes through with much less area. So even though the combinatorics of the code says these cycles have to be big, how do the combinatorial cycles, how do we know the smooth cycles can't cut corners? And of course they can cut corners, but we only have to argue that it's a bounded amount that they can cut corners by. So the key lemma is an isoparametric lemma, which has an amazingly simple proof, but we were not able to find this or even talk to analysts who knew this statement. So let me just write the key lemma, and you'll see how it's used. So the key geometric lemma is, suppose C is a chain, and it's a chain of dimension k in Bn, where Bn is the unit ball in Euclidean space. We can normalize to that. Unit ball in n-dimensional Euclidean space. And suppose the boundary of the chain is in the boundary of the ball. Then the claim is there exists another chain of the same dimension, C prime, with the same boundary, such that the K area of C prime is less than some constant, depending only on dimension, of the area of C. So in pictures, suppose we have a chain with boundary out here on the boundary of the ball, and it goes all around in the ball. The claim is we can find a chain on the boundary with not much more area, maybe even less area. Now, the way you prove this, I mean, the way you want to prove it is you want to just take some point in the ball and project out to the boundary. But you see, if the point is very near the chain, then the area gets blown up. You know, so the chain could, for instance, coil around and around and around at some point, and when you project, it goes nuts. But the key is to think about a little element of area, little element dA, and then projection from a random point P, and look at its area and the expectation value as you vary over P. So there is a divergence. If your point is very near the chain, its visual image diverges. You get a 1 over rho to the k blow up. But when you integrate over the ball, you get a rho to the n minus 1 d rho d theta. And these, at worst, give you a constant. So in other words, the expected expansion of an element of K area is bounded over a random choice of point. And now you use the linearity of expectation value to analyze the expected expectation value of the entire chain as an integral over the expected value of its tiny dA segments. And the conclusion is that a random point will do. If you take a random point in the ball, actually it's good to take a subball of radius 1/2 and project from that. There's a bounded expansion of area. So it's very short, lovely fact. And the reason it's the key fact at this moment is the staircase that I was drawing. This is what we have to push into. And what we have is we have our smooth chain. And we have to push the smooth chain inductively, dimension at a time, cell at a time. We have to push it into the cell structure that we've built. Well, this is done by millions of little operations inside each cell, and all the cells are quasi-isometric to a Euclidean ball. And in each one, we accept this constant expansion, but you can just estimate it's just the power of those constants. And by the time you've succeeded in taking your supposedly small area systole and pushing it into the combinatorial cell structure, it's only been expanded by at most a bounded amount. So that's kind of the link which between the Riemannian geometry and the combinatorics of the code. The combinatorics of the code gets encoded in an explicit cell structure within a Riemannian metric, which is a bounded local geometry, which is a direct consequence of the sparseness of the code. And then the way you analyze the relationship between cycles in the manifold and combinatorial objects in the code is by this projection lemma. So it's one, maybe I should stop. Maybe the last thing, the little unfinished business, which I didn't quite get to, is if you're interested, you might check an appendix. An appendix to the paper, we prove what we call a decongestion lemma, and it seems like a nice fact in graph theory. The fact is, and this is an argument of Matt's, I watched him basically over Skype come up with a proof, and it was beautiful to see. Learned a lot just watching him think. So the statement is, if you have a sparse graph, which you can think of as a graph with bounded valence, then you can come up with a bunch of loops, a set of loops, which are a free basis for its fundamental group, with the property that no loop goes over very many edges. The number of edges, each edge, sorry, I didn't quantify that right. If you look at this family of loops, which constitute the free basis, the statement is that no edge needs to see more than log v squared number of loops. So in other words, what you avoid, if you do kind of a boring algorithm, you run the risk that some edge is like in every basis loop or something like that, which would violate the spirit of low density parity check. It would violate bounded local geometry and sparseness. So we wanted a way to remove the fundamental group, which is created during our attachments. We create a free fundamental group, and we needed a way to remove it without adding congestion. And we found a probabilistic algorithm for constructing a cycle basis, actually a free basis for the fundamental group with that property, that sparseness property. Okay, so I think that's a good place for me to stop talking and go to questions.
Wonderful, thank you.
Thank you, guys.
Questions for Mike? Oops. So at the end of the day, you construct then this family of Riemannian 11 manifolds that has the topology S4 cross S7 with what you called 4-7 systolic freedom, is that?
Yeah, well, yeah, let me tell you exactly where we are now. Yeah, so at the moment, what we have is a family of 11 manifolds, of Riemannian 11 manifolds, and they have different smooth topologies a priori. But as you move through the family, this systolic ratio goes to infinity, and it goes to infinity as a power law, in the strong way. And using the latest codes, which I just heard about yesterday, that alpha is 1 now instead of quarter. So it's a very strong family. Now, the unfinished business is it would be nice to put these all on one fixed smooth manifold. And our target smooth manifold is S4 cross S7. Just like in my early paper with Feng Luo and David Meyer, it was S1 cross S2, so it's very similar. And in there, we did some low dimensional surgeries to do this and show that they didn't affect the geometry that much. Here, we really need to know a little bit more detail about the lifting of the code. So Greg's point about is actually very relevant. So what we would need to know we need to know two things. One is, remember I said that when you take the lifting, it's a little tricky even at the start to get sparseness, to keep the lift sparse when you lift. But we know how to do that. But one of the things that doesn't seem to be true in general is that it seems possible that you introduce odd torsion in the homology and cohomology if you do a careless lift. And if you do such a lift, then the manifold would turn out to have torsion in its homology groups. It wouldn't be like S4 cross S7. So we'd like to prove that for the particular codes that we're lifting, that we can do it without creating torsion in cohomology or homology. And I think that's true. It looks that there's a lot of freedom in choosing these lifts. And again, probabilistic arguments are the way we think about it. And there just have to be phenomenal accidents happening in order for all the lifts to create torsion. So we think that's very unlikely, but we don't have a proof. Then if we do that, the next thing that has to be done, which is really a funny thing from the point of view of coding theory, is in coding theory, you want codes with high rates. You want to encode a lot of logical qubits. But in order to make a simple mathematical statement that the manifold is just S4 cross S7, we actually only want 2 qubits in there. So we want to eviscerate the code. So we want to make the code have a very low rate in order just to have this one simple manifold without hurting its other properties. And of course, coding theorists would say, come on, why do you want to damage a great code, you know? But, you know, to show it off in this mathematical form, we want to damage it, but not enough to hurt its other properties. So that's the last step, to have one simple manifold.
Okay, thanks. We have a question from Nicholas.
Hi. Hi. Can you hear me?
Yeah.
Yes.
Thanks for the nice talk. So I've got a question. In the opposite direction, so if you want to kind of increase the dimension of the manifolds, like, would it help you to have like, so you explained that you can think of CSS codes as length 3 chain complexes. Like, would it help you to have like chain complexes which are longer? And could you kind of use your construction to kind of get higher dimensional systolic freedom?
Well, yeah, no, for instance, it's very easy to go up in dimension. That is, okay. Everything I said, once J is 4, you could just move it up and just change the indices. You wouldn't have to say any new words. Oh. But so that part is easy. But sorry, what was the? Is there
so
still?
The question was essentially, okay, I think you already answered it. So my question was, like, would it help you to have chain complexes which are longer?
Yeah, no, I did want to address that. We also have thought about arbitrarily long chain complexes, and those can be lifted preserving sparseness, but then these same questions about torsion come up, and sparseness and torsion. Yeah, so we know how to lift a complex in general, but it may not be sparse. But for particular codes, we see how to preserve sparseness, and we're on the cusp of torsion, understanding torsion. But what I wanted to make a general remark about sparseness, which is, you know, what is algebraic K-theory? It's basically linear algebra where you keep track of some group theoretic periodicity, like that's what Whitehead groups are about. Can you do certain row operations equivariantly with respect to the action of a group? You know, can you find these equivariant operations to reduce matrices to some trivial form? You know, that's basically what the Whitehead groups are. And so, you know, this has been hugely influential in topology, thinking about linear algebra done equivariantly. Now it's kind of in my consciousness, at the top of my consciousness, that there's another adjective that can be added to linear algebra, which is sparseness. And you could ask all kinds of questions about doing linear algebra equivariantly and now with sparseness preserved. You know, just that's a new parameter. And it seems like you can now revisit all these old questions. So for example, one theory in linear algebra is geometric localization. That is, or geometric control. You know, can you do row and column operations, maintaining control with respect to some metric space, which is the reference space for the basis elements. This is the way, you know, this is like Frank Quinn's life work on geometric surgery theory. So I think I think this whole subject can now be, also you can add sparseness. You can say, can you do all these things preserving sparseness? Are there obstructions to adding sparseness? You get a new kind of K-theory.
Okay, thank you.
Greg Cooperberg has a question. Greg.
I remember before, Mike, you were really focused on fault tolerance with material science rather than you know, engineered fault tolerance. But in this whole talk, you're clearly I mean, it's not for the same purpose. You're doing it for applications to higher dimensional geometry, but you're using something that is coming from engineered fault tolerance instead of material science fault tolerance, or software fault tolerance rather than material science. So you could say, well, yes, this is just for the purpose of doing geometry topology, but I'm wondering whether your thinking has shifted on which avenues for quantum fault tolerance are actually important.
Yes, yeah. So I want to give the audience some context to Greg's question. So 20 years ago, I believe, I don't know the exact date, but very close to 20 years ago, Greg said something extremely prescient to me. He said, there are guys like you, I was already had identified myself, who are asking about physical level or material science or condensed matter physics level fault tolerance. That's topological phases. And then there are guys like Preskull and who are talking about software tolerance, letting the qubits make all kinds of errors and just fixing it up afterwards. And what Greg said is, I don't think there's really a whole world of difference between the 2 points of view. And in fact, I would guess that the ultimate solution will be a hybrid between physical and software. And actually, Greg, I think you were right. So the reason for saying this is we found in our quantum program that topological phases are extremely hard from a engineering point of view. And I think the vision that they're a shortcut to error correction is probably mistaken. I think they can be an aspect of error correction, but they're not a panacea. I think there's like a conservation of pain going on, and quantum computing is hard on all accounts.
Of course, all of the CSS stuff is still additive, and so that you're not natively universal anyway with.
Well, but I mean, that's true. I mean, what you're thinking of is like Clifford operations aren't natively universal, but if you have some kind of quantum computer, like say of the Google sort, they would certainly expect to wrap it up in a CSS code so that, their qubits are like 3/9 of fidelity or something, and then maybe a ratio of 10,000 to 1 physical.
Well, actually, that second part, more than the first part, which was not meant as rhetorical adequacy, but for this second part, you have this loophole that you can use modular tensor categories and non-abelian anyons to get something that's LDPC but not additive and natively universal. And then the first example is Fibonacci Terray-Varot.
Right.
And then you do get the systolic business even too, if you want that, but only, as you said, with a logarithmic victory. And I simply don't know of anything that you can do in higher dimensions than 2. But 2 dimensions is enough to already get somewhere. If you wanted to be, I forget the phrase for it, staying in code and universal.
Yeah. Yeah, no, those are good points. I mean, 11 manifolds are obviously not very engineerable. So this is really theoretical. In terms of dimensions and stability, I wonder whether, even though it sounds much harder, I'm wondering whether if one really wants to lean on topological phases in order to do the guts of the computation, I'm wondering if 3 dimensions isn't better because of the connectivity. That is, quasi 1 and quasi 2-dimensional systems seem to have very disappointingly low gaps, spectral gaps, protecting this protected subspace. You might imagine that higher coordination from lattices and interactions in higher dimensions would be better.
I wasn't considering a surface with genus 1000 to be very engineerable either. I would still take it seriously as a candidate for software fault tolerance, even if what you're doing is simulating Fibonacci-Touré-Virot, for instance.
Right, but what I'm
but
saying, I'm just thinking that the Fibonacci, two-dimensional Fibonacci anyons are likely, in any model I know of, to be very fragile. And I would imagine that there might be 3+1 dimensional TQFTs that could be engineered with a much more robust structure.
So there was just a paper out that I found in the archive from Eagle Googling just a few weeks ago, where they asked how fragile it could be if you have the freedom to decide your fault tolerant error correction protocol yourself. And they claimed that they could simulate a multi-scale error correction algorithm to get rid of the quasi-particles for Fibonacci-Touré-Virot with a high fault tolerance constant.
Why don't you forward that to me? I'd be really interested.
So, but here's where I'm stuck, which is that I don't know of any codes that are sufficiently non-additive to be internally universal for QC beyond 2 dimensions. So that's my question. That's a question. Are you really stuck with 2 dimensions? Maybe a surface that's very high genus, but still just a 2-dimensional thing for that. If you wanted, if you had all of those requirements for what the code does.
No, I don't think so. I mean, for instance, even this the group representation codes, what are those called? Sorry, what are the names of the physicists and the codes that
you mean digraph?
Digraph Witten, yeah, the digraph.
Okay, we could ask Ed. He's in the
I think that those codes, even for like the symmetric group on 3 elements, are universal, right?
Well, they are, but you see, it's not the degree, the homological degree. You're using non-commutative first cohomology, in effect. So even if the dimension of the space is large, you don't have this middle degree advantage for what you were just talking about. The degree is pinned at one end.
So let me try to sneak in maybe 2 more quick questions.
Okay. Yes, go ahead.
Yeah, so Shirar,
Hi, yes. So my question is about the toric code, and I just wanted to understand the way you explained the accumulation of errors in such a code as the thing changing its homotopy class. Can one think of errors as an action of mapping the class on the underlying grid or the underlying code on the torus?
No, one errors is the mapping class, but the logical operators is the mapping class group. So I think the way to think of it is, maybe the easiest way to picture it is to think of that you take the 0, 1, ket 0, ket 1 basis, and in that basis, so just consider states which on every edge are labeled 0 or 1. And then if you look at, with respect to the star operator, that's enforcing it's enforcing even valence at every vertex. And now if you have a single error, what that does is that's like acting with the X operator on one of the bonds, on one of the edges. And mod 2, that just erases or changes the flavor of that edge. So if that edge was white, it becomes black. Was black, it becomes white. And what that does is it produces 2 violations. If the system of edges originally has even parity at every vertex, and you monkey with one edge, then the 2 vertices that were at the ends of that edge, now they show up as violations. So those are where you see errors. And now you have to see a lot of errors in order to forget and not be able to recover what the homology class of that cycle was. Basically, if the smallest cycle has length d, once you see about d over 2 errors, then you can no longer tell whether the cycle wrapped around or didn't wrap around.
Right. Okay.
So,
But can you tell what the cycle changes by? By which class? Maybe.
yeah. So, I mean, a logical operator, what the smallest logical operators, these would be like put sigma x on along a systole. And then what it would simply do is it would Dane twist, if you like, around that systole.
Mhm.
Or another way of saying it, it would add a copy of that systole to the homology class that you originally had. So it would give a linear operator on, it would be a linear map on H1 with Z2 coefficients, and it would be the induced map then on the Hilbert space.
Right. Cool. Thank you.
So maybe one last question by Mason. Go ahead.
Oh, hi, Mike.
Hey, Mason, good to see you.
Thanks for the talk. So I was curious, you mentioned the encoding rates, but can you build a manifold that preserves the encoding rates?
Yeah. So in other words, I was saying that to get down to like S4 cross S7 is like a parlor trick,
Yeah.
you know, to have a clean statement. But it's actually more interesting if the sequence of manifolds is well, all this is about a sequence of manifolds, right? Or a sequence of metrics. And what would come out naturally is like the first one would be a connected sum copy of 10 copies of S4 cross S7. The next one in the sequence would be connected sum of 100 copies and then 1,000 copies. It would grow like that. But then the systolic ratios would be diverging as you went out through the sequence. That would be the natural conclusion once we solve the torsion problem. And where we are right now is we don't even know the manifolds are connected sums of these very simple pieces because they have some torsion in the homology, and it's a little hard to analyze them.
I see.
Okay, so the next talk in this series is in 2 weeks, and we'll go back to an every 2-week schedule. The next speaker is Albert Clem. So the discussion can continue after, but let's thank Mike again for a very stimulating talk.
Thank you, guys. And thanks, Dan, for organizing.
Well, fellow organizers too.
Okay, sorry.
No problem. Okay, I stopped recording, so you can go on. If someone has
We can
questions.
unleash the profanities now.
Well, there you go. I think I stopped. Yeah, I did stop recording, but it's still on YouTube or something, so be careful. So in this area of kind of